So this work the title is Sequential Recommendation for Optimizing both Immediate Feedback and Long-Term Retention. And this work is mainly done by City University of Hong Kong and Qingpeng. So let's start with this. Before introducing the methodology, I prefer to start with the background. So sequential recommendation systems have received considerable attention due to their importance role in real-world applications. The success of sequential recommendation system heavily relies on users' engagement on the platform, which is reflected by the user's immediate feedback, like the user clicks and user likes. However, they cannot completely review users' preferences. So that's why we need to optimize the user's long-term engagement, which we call the user intentions. So as a tool for optimizing long-term metrics, offline reinforcement learning has been widely studied for optimizing user intention in recent years. So that's why we are going to do this work. However, the existing reinforcement learning-based sequential recommendation system have several challenges. First, we may face the deadly trailed problem, which means the reinforcement learning model becomes unstable when the function optimization, bootstrapping, and off-policy training are present at the same time. So second, the single reward setting for basic reinforcement learning problem cannot match our need for optimizing both long and short-term user behaviors. So therefore, in this paper, the authors propose to apply decision transformers to sequential recommendation system. The decision transformer models the user's interaction trajectory as a sequence, transform it into a supervised problem. This method skips bootstrapping, avoiding the deadly trailed problem, and eliminates the need for policy evaluation as a training time. However, there are some challenges implying the decision transformer to the multipath learning framework. First, we need an efficient multi-reward design so that can extract the hidden relation between immediate feedback and the retentions. Second, the decision transformer uses a simple embeddings for rewards, which can lead to low-quality recommendations. And therefore, we propose this novel decision transformer-based model called DT4IER to solve these problems. So below, I will introduce our problem definition. We will use decision transformer to optimize both click-through rate and user intention measured by user return frequency. A user trajectory consists of cumulative rewards, or so-called return to goal, the status, and also the actions. So here, the T means the specific sessions, and we define them as follows. The state ST actually represents the historical interaction information with length n, and the action at this point is the recommendation item based on the state information. And the reward contains both the click-through rate and the return frequency. Yeah. So, and overall, the return to goal RT is the non-discounted cumulative reward from the sessions T to LART and calculated by this formula. And given the state informations, we try to take actions that can maximize the expected reward. Yeah, so this is the whole framework of the proposed methods. It actually consists of four main modules: the RTG balancing block, the embedding module, and transformer decision block, and action decoding block. So in the following part, we will introduce these explanations of each part. And so the first part is the adaptive RTG balancing module. To effectively capture the dynamics of short-term and long-term user behaviors, we propose to apply user feature-based reweighting to the RTG sequence. We propose the categorical features through an embedding layer. Meanwhile, the numerical features are refined using a multi-layer perceptron. The combination features vectors is further processed by another multi-layer perceptron with softmax activation function to get the weight for each reward. And to get the optimization process, we try to maximize the overall weighted sum of immediate reward and the retention reward, which corresponds to the first term in the balanced reward loss. We also implement L2 regularization term, which imposes a penalty on deviations between the weighted rewards. Such a strategy is designed to prevent the system from one type of reward over the others. Yeah. So since the prompts generated by decision transformers should maintain the partial order relations between the rewards, we propose to generate more efficient prompts by the auto-discrediting method. Specifically, we first average the reward values into buckets, and we train the meta-embedding for each bucket value. Then we convert the reward into a weighted score from the learnable embeddings. Given the weighted score, the reward embedding is set as the aggregation of these meta embeddings. As for the states and actions, we both use GRU as an encoder to map the dynamic length of the interaction sequence vectors. And to learn user interests from their interactions trajectories, we utilize transformer decision blocks, which consists of the unidirectional transformer layer, the skip connections, and the feed-forward neural networks. And given the contextual information of atoms interacted at each time step, as the action decoder aims to decode the sequence of atoms of interest to users with the GRU model. Since there is no information for predicting the first atom, we use the token S as the start marker. In the decision transformer, only the maximal rewarded actions are used for inference. And this means valuable insight from low rewarded actions may not be fully utilized. So we propose a weighted contrastive learning approach that treats low rewarded actions as negative examples to avoid recommendation them. The final objective function is calculated as the cross-entropy loss from the recommendation and also the contrastive learning term. And finally, let's talk about the experimental part. We conduct experiments on 3 data sets, Querent Pure, which is an unbiased data set, and movie lens 25 millions, and retail rocket, with more details present in this table. And you could see these data sets are all large data sets. And we evaluate our proposed model's effectiveness using various metrics, focusing on both the recommendation accuracy from the blue to NDCG and also the user retention score. For the baselines, we compare the performance of our approach with SOTA models spanning both multitask learning and transformer-based sequential recommendations. And so this is the overall recommendation results. And among all models, MMOE demonstrates the worst performance for both recommendation accuracy and retention, since it actually struggles to adapt to the dynamic of sequential data. So it performs worse. And in all the baselines, DT for RAG achieves the best performance among all baseline models. Its unique design guides the model training towards boosting long-term user engagement, thus will enhancing the user intention score. And our proposed model consistently outperforms the 4 baselines in both the recommendation accuracy and the retention score for all datasets. By interpreting reinforcement learning as an autoregressive setting and integrating a structure designed for multiple rewards, our model reaches a balance between the immediate feedback and also the long-term retention. And for the evaluation study, we conducted to show the significance of the specific models in our proposed model. Here are the 3 variants we define. NAW represents the model variants without adaptive RTG weighting models. And NRE means we use standard reward embedding. And NCL means we use objective function without the contrastive learning component. And the results shows that the lack of any module will significantly decrease the performance of the decision transformer models on both recommendation accuracy and the user retention score metrics. And especially the NRE variants, and this underscores the effectiveness of our RTG embedding model. And for the inference of the decision transformer is conditional on the highest possible return to goal values, which is the RTG values. However, in practice applications, this ideal scenario isn't always achieved. So we utilize RTG prompting with a reduced proption to improve model performance. The best performance is achieved at an NTG proption of 0.8, and the result exactly validates our hypothesis regarding the RTG prompting. And for the case study, we also highlight that our model is effective in improving the recommendation performance through a case study on the QuiRank pure dataset. Which is an unbiased dataset that all the videos are randomly exposed to the users. And given user state and the goal of maximizing retention, DT4Rec recommends these 3 videos. And in contrast, our model outperforms by recommending 4 videos, all of which align with the ground truth action sequence. And this result underscores that our model's enhanced efficiency attribute to a simultaneous consideration of short-term clicks and the long-term user retention information. And for the conclusion, and in this work, we introduced the DT4IER and advanced decision transformer method for sequential recommendation in a multi-reward setting. And it leverages a novel reward design that integrates immediate user response with long-term retention signals. Furthermore, the reward embeddings module is enriched by a high-dimensional encoder that navigates the relationships between different tasks. So that's all for this paper. Thank you, everyone.